Thank you. All right, so I'm Patrick. I work at Sandia National Laboratories, and I work on our computer architecture simulator, SST. And so I found a really nice use case for Spack that I wanted to talk to you today. It's going to improve reproducibility and usability for our simulator. Short outline for this talk. I'll give the motivation for this work, give just one slide of background on what our simulator is and the component I want to talk about, which is called Aerial. I'll talk about sort of this project, SST-Apps, go over some of the benefits expected and unexpected. Then I've got a little bit of follow-on work that'll be really cool. Spack adds a couple more features that I think are on the roadmap, and then I'll do a summary at the end. So, quick motivation. The problem we face is that getting applications up and running in your simulator is a time-consuming process. It's often very manual, and manually building and adding simulation markers is going to lead to reproducibility issues when someone built the input program in a different way. As well, you need to spend time identifying your critical regions, saying here's what I want to simulate. You have to mark that in your code typically. So that's a time-consuming process that slows people down from getting that simulator up and running. And all that time spent on getting benchmarks to run is time spent not doing research and running your simulator and looking at results, etc. So my goal is just to release a set of simulation inputs for SST and to enable users to easily run them. So I want to have these reproducible inputs, and then I want it to be easy so people can start using our simulator that much faster. Anyways, yeah. All right. So let me talk just for a second about what our simulator is so I can give a bit of context. The Structural Simulation Toolkit is this parallel discrete event simulation framework we maintain at SST. It's an open source project, at Sandia, it's an open source project. And it includes lots of simulators for CPUs, memory systems, accelerators, networks, and more. And then what you'll do is to use SST, you'll take these different components and wire them together, and you'll create your model of your computer system that you want to simulate. One of these components, and sort of the focus of this talk, is the Aerial simulator, which is a trace-based CPU simulator. It's part of SST. To give a bit of high-level overview of how Aerial works, you can see over on the right side here, Aerial takes a natively executing application, grabs those memory references, so it captures all the reads and writes, and then it sends them across a shared memory tunnel to a Aerial front end, and so everything down here at the bottom, that's your simulator. So it captures these memory references from a native running program. And now it sends those down, they get sent to their cores, they get simulated, right? Aerial uses a really simple API, Aerial enable, Aerial disable. There's a couple more, but this is the basics. So these are the calls that you would need to add to your program before you simulate in Aerial. The point here is that Aerial is a natural fit for Spack. Applications need to be compiled to run natively. That's something that Spack can help us with. And as well, we would like reproducible inputs so we can have reproducible simulation results, which is a big, I would say, issue in computer architecture simulation in particular. Okay, so let me get to the actual Spack part of this talk. SST-Apps is a repository of benchmarks that have been verified to work with Aerial and modified to include these simulation markers. SST-Apps is released as a Spack package repository. It's on GitHub, and it was actually very surprisingly easy to get all this to work. So because Spack allows you to extend the package files in the built-in repo, we can pick from benchmarks that are already there. We add our simulation markers where we need to, and we can just publish the changes as a patch. So this saves us from having to fork all of these and have, if we want 10 benchmarks that we want to release, we don't want to have a bunch of forks living somewhere with tiny changes, so we just have these patch files as part of our Spack package repository. And then we have to do a little bit of linking as well, but that's okay. You edit the CMake. And so the result of this is that now we can release our inputs for our simulator with very little infrastructure. We just have this GitHub repo. We don't have to do something really complicated where we're setting up an external resource to set these up. We have this nice Spack repo, and it's worked really well. And I guess one limitation is right now just aerial is supported. We have lots of simulators in SST, and in a couple, at the end of this talk, I'll talk about what would be really cool to add support for more simulators. So this is the ones that I've supported so far. So just some sort of basic HPC type benchmarks. And then that last one there, anything with caliper is going to be supported very soon as well. And that was sort of one of the unexpected benefits, and I'll talk about that on the next slide or two. And yeah, to use it, it's really simple. You just use the standard Spack commands. You can add our repo. You would install the aerial variants of these benchmarks, and then you're ready to go with that last line there. You can run your simulator, and you've got all these inputs available to you. Okay, so just wanted to talk about the benefits of doing this work. The expected ones, right? We have made aerial easier to use. We are leveraging Spack's ability to do reproducible builds and using that to enhance our computer architecture simulation research. And as well, we get to encourage the use of our favorite benchmarks. We can sort of put our finger on the scale and say, here's some good ones that you should consider using in your research by making sure those are available to our users. The unexpected benefits, one thing I didn't anticipate when doing this is that because SST is available in Spack, the simulator itself has been available for years in Spack. Now that we have inputs that are there too, Spack's testing becomes a natural place to do integration testing to ensure that these programs continue to run in our simulators. And I have a few of these implemented. The full list doesn't have integration testing, but something I'm working on. The second unexpected benefit is that we can use all the apps that already have caliper integration, and we end up with a really cool simulator validation workflow that I'll show off as well. Okay. Go back one. All right, so caliper integration. So caliper, a slight detour, but still a really cool benefit of integrating with this, of using Spack is that caliper is this lightweight code annotation library and performance analysis toolkit from Lawrence Livermore. And it provides hooks for many languages and tools, including Cocos. And soon it will have hooks for aerial as well. So I showed off earlier, aerial enable, aerial disable. If someone has already added caliper to their app, now you don't even have to do that. Now you can simulate in aerial by just using the aerial connector, which will be part of caliper. And we'll still want to extend these packages just so we can do the integration testing. And just to, I guess, show off caliper, many of you will be aware, but I think it's a really cool tool, so I was just showing it here, is you can ask for all these really cool reports on your code. You get a runtime report to see where time was spent. You get a loop report, an MPI report, CUDA report, and then this one that I've added is the aerial connector. So you can turn this on, and if your code has these caliper annotations, now your code can be simulated in aerial. So that, I think, is a really cool usability as well. And the real cool part, I think, of this caliper integration is that now you get this nice validation workflow, simulation validation, another sore spot in computer architecture simulation. So this workflow, you can build caliper with your aerial support, of course, annotate your code once, or maybe it's already annotated by someone else and it's available on Spack. And now when it comes time to validate your simulator, say you have a Sapphire Rapids box, you also made a Sapphire Rapids model in SST, you can just run the same thing natively, get your caliper report, and you can run it in your Sapphire Rapids simulator that you built with Aerial. And you get this really nice one-to-one comparison, makes validation of your simulator much simpler when you can do this sort of one-to-one comparison. So this is a big usability update for SST. Okay. So that's what works so far. We've got this cool caliper integration. We've got this nice SST-Apps package repository. That only works for Aerial, which is just one of our simulators. We have many. And there's two others that could really benefit from this. The first one is called Venatus. This is an out-of-order RISC-V simulator that's available in SST. Now, running programs in that requires downloading the RISC-V toolchain, doing your cross-compilation, etc. If Spack gets cross-compilation support, or I suppose when it does, that's going to enable us to do this same sort of workflow with the Venatus RISC-V simulator, so that'll be really cool. Another one is Mercury. This is an MPI simulator. In Mercury, applications are executing natively, but they require a custom compiler to do some setup stuff. So I think that may or may not need Spack's cross-compilation support. I'll have to think about it a bit more. But that'll be really cool. This is just going to make it so much easier to get up and running on a simulator. So that is what I've got for you. The SST, in summary, SST-Apps makes installing simulator inputs easy, allows us to release this app by standing up, very little infrastructure, and it improves usability and reproducibility in SST. One of the unexpected benefits was we get this integration testing using Spack. That's more powerful than what we can do with our built-in SST testing. We get this caliper integration, and that is going to give us easy access to caliper annotated apps, and it improves simulation validation. And as well, there's some exciting, future possibilities that we can add in the future. So that's what I've got for you. There's my info, and thank you very much for your time.
We have time for some questions if folks have them.
Just a quick clarification question based on the layout. Aerial is an element of SST, is that correct?
Yeah. Aerial is released as part of the SST elements, which is where all of our sort of simulation models live. Yeah.
What do you think are some of the things we're going to need to handle for cross-compilation for simulators versus cross-compilation for, say, like building on Fugaku with an x86-64 ARM?
We use a pretty unmodified RISC-V compiler, so I think nothing special is going to happen for RISC-V. For the Mercury stuff for HGCC, that's unclear to me what it'll need, because it's a special thing. I don't know. I haven't worked with that one personally. Yeah. Yeah. No, I know it's on your roadmap, and I thought this is one more cool use case for it, so wanted to share that. We should get Joe Kenny involved. I think if we're going to when we talk about the Mercury stuff, I'd like to figure that out. That's a compiler that it also ships with SST, and so we need to use it as well as a compiler. Yeah, thanks.
This might be testing the edge of your knowledge, but is HGCC like an MPICC like, can I call it like MPICC? Is it like the MPICC wrapper, and then therefore would I be able to use like CMake and pull the actual like compile line off of it, or is it like very different?
HGCC does this weird thing where it turns your multi-process into execution into it executes a bunch of processes as user space threads. So we do that to increase the scalability. You have to do it does a lot more where you have to rip out. You try to rip out memory allocation and stuff like that that we ideally would not do in simulation. So it does a lot, but yeah.
Okay, we've probably got time for one more question, and also, Jake, can you get ready? There you are.
So this is just kind of like a general question about SST, like what kind of simulations do you run? Because I think there's some elements of like performance that are like hard to get at or have too much jitter. So like so for example, like what amount of slowdown is there in simulating something with SST versus a real world system? And what are example, like a span of problems that you can get at?
SST includes many different types of simulators. You can do just a dedicated network simulation. You can do these trace-based CPU. You can do execution-driven CPU. So we'd have to talk about what type of simulation you want to run. Yeah. Thanks.